All right, lesson 10. This is day 15. So make sure you have lesson 10 out so that we can go through this. Make sure you are copying down what we're doing. And then if you have any questions, reach out to me, guys. All right, so let's look at exercise number 1. It says, consider the statement, the President of the United States is a United States citizen. Is this sentence, or is this statement a grammatically correct sentence? What is the subject of the sentence? What is the verb of the sentence? Is the sentence true? All right, so we're going to look at this and just very quickly go through this. The President of the United States is a United States citizen. Is it grammatically correct? Yes. What's the subject of the sentence? President. What's the verb of the sentence? Is. Is the sentence true? Yes, it is. All right, so yes, President. The verb is. And is the sentence true? Yes, the statement has to be true. All right, you have to be a United States citizen in order to be the president. All right, look at the second one. The President of France is a United States citizen. Is the statement a grammatically correct sentence? Yes. What's the subject of the sentence? President. Verb is. Is the statement true? No, it is not true. Because if they're the President of France, they should not be a United States citizen. All right, consider the statement, 2 plus 3 is equal to 1 plus 4. This is a sentence. What's the verb of the sentence? What's the subject of the sentence? All right. And I know this is kind of weird because you're in my class and we're talking about English, but believe it or not, we do have a subject here. The subject of the sentence is the numerical expression 2 plus 3. All right? So the subject is 2 plus 3. So what do you think the verb is? Well, the verb would be equals to. All right, so 2 plus 3 is equal to 1 plus 4. It is grammatically correct. All right. Is this sentence true? Well, I need to look at this. 2 plus 3 is equal to 5. 1 plus 4 is equal to 5. So is this grammatically true? Or is this sentence true? Yes, it is true. All right, and then the fourth one. Consider the statement 2 plus 3 is equal to 9 plus 4. Is the statement a sentence? If so, is the sentence true or false? Well, is this a sentence? Yes. So 2 plus 3 is our subject. Equals 2 is our verb. But is it true? So yes, it is a sentence. But is it true or false? Well, 2 plus 3 is 5. 9 plus 4 is 13. Are those equal? So it is false. All right? Now, if you'll go back up and look at the title of our lesson, True and False Equations. So hopefully that kind of gives you an insight as to what we're doing here. All right, so let's look. Here's some definitions. A number sentence is a statement of equality between two numerical expressions. A number sentence is said to be true if both numerical expressions are equivalent. That is, both evaluate to the same number. It is said to be false otherwise. True and false are called our truth values. Okay, that is our truth values. All right, let's let's move on. So we are going to determine whether the following number sentences are true or false. Alright, now remember, in order for them to be true, both sides have to be equal value. If they're not, then they are false. So let's look at this. 8 plus 4, that's 12. 10 plus 5 is 15. Is this true? Well, is 12 equal to 15? That is false. Alright. B requires a little bit of work here. Alright, so I need to figure this out. So let's look. We're adding fractions, which means I have to find common denominators. 2 goes into 8 4 times, so 4 times 1 is 4. The second fraction did not change. Alright, so I have 9 eighths is equal to, and now I'm going to take 1 and 2 tenths minus 0 and 75 hundredths. And when I do that, and guys, you can use a calculator on this, I get 1.125 or 1 and 125 hundredths, or thousandths, sorry. Alright, so taking my calculator, I'm going to divide 9 by 8, and look at this. 1 and 125 thousandths is equal to 1 and 125 thousandths, so that one is true. Alright, so let's look at C. C actually does not require me to do much of any math. I can actually look at this as my properties. Guys, look at this. 71 times 603, and then multiply that times 5,876. 603 times 5,876 times 71. If you look at this, I can actually use the commutative and the associative properties. Guys, my numbers never change. I have 71 on both sides. I have 603 on both sides. And I have 5,876 on both sides. So the commutative and associative properties of multiplication show me that this is true. Alright, and I'm going to write this down because, like I said, we don't even actually have to do the math to know that they are equivalent. Alright, let's look at this. 13 times 175 is equal to 13 times 90 plus 85 times 13. You can work it out. You can do however you would like to do. What you're going to see is that it is true, because what's happening here, I'm multiplying 13 times 90 and 13 times 85. So look at this. I can put parentheses in that. What is 90 plus 85? It's 175, so I'm multiplying 13 times 175 on both sides. So that is true. Alright, E. 7 plus 9, and then I'm going to square that, is equal to 7 squared plus 9 squared. Use your properties of exponents to tell you actually what's going to happen is I'm going to add this first before I square it. So that would end up being 16 squared. And remember, I'm putting a question mark over equals because I'm not sure that they're equal yet. Is 16 squared squared the same as 7 squared plus 9 squared? If all else fails, figure that out. 16 times 16 is 256. 7 squared is 49, and 9 squared is 81. So when you add 49 plus 81, you only get 130. So they are not equal. This is false. All right, it says that pi is equal to 3.141. Here's the problem. This is actually false because pi does not stop at 3.141. It continues on and on and on. So pi would equal 3.141 ... because it tells me that it never stops. Pi never stops. So I cannot say pi is equal to 3.141. If I wanted to, I could say pi is approximately 3.141, but it is not equal to that. All right, and then g, the square root of 9 plus 4 is equal to the square root of 4 plus the square root of 9. Well, let's look at this. What is 9 plus 4? That is 13. The square root of 2, or square root of 4 is 2. And the square root of 9 is 3. Remember, square root is something times itself. Gives you that number. So does the square root of 13 equal 5? That is false. All right, h. Let's look at this. 1/2 plus 1/3 is equal to 2/5. So basically they're saying all you do when you add fractions is you go straight across and add. We all know that's not true. 2 and 3, our common denominator would be 6. So therefore I automatically know this is false. All right, let's look at I. 1/2 plus 1/3 is equal to 2/6. Well, I have to figure that out. So we'll make 6 our common denominator. 2 times 3 is 6, so 3 times 1 is 3. 3 times 2 is 6, so 2 times 1 is 2. It does not give us 2/6. It would give us 5/6. So that is false. All right. 1/2 plus 1/3 is 5/6. We've already figured that out. That is true. 3 squared plus 4 squared is equal to 7 squared. 3 squared, 3 times 3 is 9. 4 times 4 is 16. And they want to know, does that equal 7 squared, which is 7 times 7 is 49. 9 plus 16 is 25. Does not equal 49. So that is false. All right. 3 squared is 9 times 4 squared times 16. And they want to know, does that equal 12 squared? So that's 144. So if I multiply 16 times 9, I get 144 is equal to 144. So that is true. All right. M, 3 squared is 9 times 4 cubed. So 4 times 4 is 16. And 16 times 4 is 64. 12 to the 6th power. So 1, 2, 3, 4, 5, 6. Does that give me 2,985,984? I can already tell you that no, it does not, because 9 times 64 is only 576. So that one is false. All right, and the last one here, 3 squared is is 9. 3 cubed is 27. And 3 to the 5th is 243. So 9 times 27 is 243. 243 does equal 243. So that is true. All right. And you'll see I'm working these out just as you are. So just kind of bear with me just a little bit. All right, so let's look at this. I want you to take just a moment, pause the video, and I want you to look at these two questions. Could a number sentence be both true and false? Could a number sentence be neither true or false? Okay? So let's go ahead and look at this. Could a number sentence be both true and false? And could a number sentence be neither true nor false? A number sentence has a left-handed numerical expression that evaluates to a single number. And it has a right-handed numerical expression that also evaluates to a single numerical value. Either these two single values match or they don't. Okay? So, can it be both true and false? No. It cannot be both true and false. Can it be neither? No. Alright? And here's the reason why. Like I said, so you have a number sentence has a left-handed numerical expression that evaluates to one number. All right? And it has a right-handed numerical expression that evaluates to a single number. Okay? So either those two single values match or they don't. Okay? So what that's telling me is when I have this equation or a number sentence, I have something on the left and I have something on the right of the equal sign. They're either going to be equal or they're not. So it cannot be both, or it has to be one or the other. All right. An algebraic expression or an algebraic equation is a statement of equality between two expressions. Algebraic equations can be number sentences when both expressions are numerical, but often they contain symbols whose values have not been determined. So this is where we get into our x's and our y's. Which of the following are algebraic equations? Okay? So it wants to know which are algebraic equations. An algebraic equation can be numbers, or it can contain symbols and letters. Alright, but it is a statement of equality between two expressions. So in other words, it's going to be something is equal to something. So let's look at this. That's an algebraic equation. equal to something is an algebraic equation. This one's an algebraic equation. This is an algebraic equation. And this is an algebraic equation. So all of them are algebraic equations. Which of them are also number sentences? All right? So which of them are number sentences? So it says, going back, if you don't remember, you can turn back here. A number sentence is a statement of equality between two numerical expressions. All right? So which of these are number sentences? Well, number 2 is, number 3 is, number 4 is, and number 5 is. All right? So number 2, not number 1, number 3, number 4, and number 5. Okay? All right. So now the next question is, for each number sentence, state whether the number sentence is true or false. All right? Pause for a moment, and I want you to figure out which ones are true and false. All right? Which means you actually have to work them out. All right? So number 2, you should see that it is false. All right? Number 3, you should see is true. Number 4, you should see is false. And number 5, you should also see as false. Okay? All right. When algebraic equations contain a symbol whose value has not yet been determined, we use analysis to determine whether, 1, the equation is true for all possible values of the variable, or, number 2, the equation is true for a certain set of a possible value or the variable, or 3, the equation is never true for any of the possible values of a variable. For each of the 3 cases, write an algebraic equation that would be correctly described by that case. Use only the variable x where x represents a real number. All right, so I want to do a case where the equation is true for all possible values of the variable. In other words, it does not matter what variable I put in there or what number I put in for x, it's always going to be true. So, I can do something like this. In this case, it doesn't matter whether I put 1 in or 500 in. Every number that I put in will give me a true statement. Okay? And that is because the distributive property shows me that they are equal values. All right? So for case number 2, the equation is true for a certain set of a possible value of the variable. In other words, I want something that gives me that one answer would work. Or maybe there might be 2 answers that work. But it's not going to be any number that I want to put in there. So I can do something as simple as this. I can say x plus 5 is equal to 11. I could put 6 in there. Could I put 1 in there? No. Could I put 10 in there? No. I could put 6 in there, and 6 is the only answer that will work. All right, and then for the third case, the equation is never true for anything. This one's a little tricky, because now I want to know no matter what number I put in for x, it's not going to work. Let me show you one. is equal to -1. And you're going, but how's that not work? Guys, if I let x equal -1, -1 squared, -1 times -1 would give me a +1. It will never equal -1. Never. So here it's never going to work. Okay? There's no real number that I can put in there. Alright. Hopefully you understand that. Alright, so let's look at example number 1. Example number 1 says this. It says, consider the following scenario. Julie is 300 feet away from her friend's front porch and observes someone is sitting on the porch. Given that she didn't specify otherwise, we would assume that that someone Julie thinks she sees is a human. We can't guarantee that Julie's observatory statement is true. It could be that Julie's friend has something on the porch that merely looks like a human from far away. Julie assumes she is correct and moves closer to see if she can figure out who it is. As she nears the porch, she declares, "Ah, it is our friend, John Barry." All right, so let's think about this for just a second. The reason this is here is because they want you to think about this. Oftentimes we observe something and it may or may not be true. Okay? And that's the same as it is in math. Often in math we observe a situation and we make a statement we believe to be true. Just as Julie used the word someone in mathematics, we use variables in our statements to represent quantities not yet known. So she used someone because she didn't know who it was. Well, what we would do is we would put an X there, or we would put a Y there, because we don't know. Then, just as Julie did, we get closer to study the situation more carefully, and we find out if our someone exists, and if so, who it is. So in other words, we get a little closer by looking at the math a little further, and we figure out, okay, is there anything I can put in for X? And if so, what is it? Notice that we're comfortable assuming that that someone Julie referred to as human, even though she didn't say it was. In mathematics, we have a similar assumption. If it is not stated otherwise, we assume that variable symbols represent a real number. But in some cases, we might say the variable represents an integer, or an even integer, or a positive integer. Stating what type of number the variable symbol represents is called stating its domain. All right, and I don't think, no. Okay, so since there's really nothing here that we need to do, I want you to write the word domain down. And that is stating what type of number the variable represents. Alright, like it said, or like I said just a minute ago, I may say it represents all positive numbers. I may say it represents all negative numbers. I may say it represents only positive even numbers. That is the domain. What does that represent? Alright, so exercise number 6. Name a value of the variable that would make each equation a true number sentence. Here are several examples of how we can name the value of the variable. Alright, so it says let w equal -2. So in that case, if I let w equal -2, then w squared equals 4 is true. W squared is equal to 4 is true when w is equal to -2. W squared is equal to 4 is true if W is equal to negative 2. W squared is equal to 4 is true for W is equal to negative 2 and W is equal to 2. So notice I underlined because this is my domain. This is telling you exactly what that variable represents. All right? There might be more than one option for what numerical values to write. All right? And it says feel free to write more than one possibility. Some of these are tricky. All right? So let's look at this. Let blank, then 7 plus x would equal 12 is true. So x would have to be equal to 5 in order for this to be a true statement. Let blank, when 3r plus 5/10 is equal to 37/2 is true. If I work this out, all right, I've got to figure out what I would put in there. And I would figure out that r is equal to 6. All right? You could solve for r. You can look at this as, you can rewrite this 3r plus 1/2 is equal to 37/2. All right? Or you can do 3r plus 0.5 is equal to 18.5. And if I do that, I get 3r is equal to 18. Divide both sides by 3, and I get r is equal to 6. Okay? M cubed is equal to negative 125 is true for, well, the cubed root of 125, that would be 5. 5 times 5 is 25. 25 times 5 is 125. But I want it to be negative, so M would have to be equal to negative 5. Because a negative times a negative times a negative gives me a negative. A number x and its square, x squared, have the same value when what? Well, what's the only thing I can put in for x and x squared that would give me the same thing? Well, x is equal to 1. Is there anything else I could put in there? I couldn't put negative 1 because this would be negative 1, this would be positive 1. But there is one other thing that I could put in there. I could put 0 in there, and that would work. The average of 7 and n is negative 8 if blank. Guys, how do you find the average? You would do 7 times x, divide that by 2, would give us negative 8. All right? So I would multiply everything by 2. So I get 7 times x is equal to positive 16. Subtract 7, and x would equal that would be negative 23. See, I make mistakes too. It's good. Let blank, then 2a is equal to a plus a is true. Okay, guys, look at this one. Remember we said that there was a case where I could put any number in as long as both sides look the same? Look at this. 2a, and what is a plus a? That would be 2a. So 2a is equal to 2a. Meaning a could be any real number. I could put anything in there. I could put 1 in there. I could put 1,000,000 in there. It's not going to matter. It would be the same. Q plus 67 is equal to Q plus 68 is true for blank. Can I put any number in there? One. That would give me 68 is equal to 69. 0, 67 is equal to 68. Negative 1, that would give me 66 is equal to 67. Is there any solution here? No. So there is no value that we can put in there. Okay, there is no value that we can put in there. All right, guys, remember, if you have questions, please make sure to ask. All right, you can get a hold of me any different way that you can. Email, Google Classroom, call the school, whatever. Just give me a call.